Welcome back to the deep dive. This is where we take some really complex stuff, research papers, dense manuals, sometimes surprising history, and try to boil it down for you. Today, wow, we're on quite a journey. It starts way back, like ancient philosophy back, and it ends up with us being able to literally see inside the materials holding our modern world together. We're digging into a stack of material titled The History of Industrial Radiography. It maps out this whole evolution, how we figured out how to use high energy physics to inspect things. So our mission today is kind of threefold. First, got to get the science down. The basic physics, what matter is how radiation penetrates it. Second, we need to track the discovery, which was like totally shocking at the time, and how quickly industry grabbed onto it. And finally, maybe the most crucial part, we'll dive deep into the safety side. The rules, the regulations, how they grew, because without that robust framework, using this powerful tech in industry safely, it just wouldn't happen, especially for you, the person actually doing the work. Today's episode is brought to you by AMS Level 3. AMS Level 3 provides consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. You can learn more about their services at the link in the video description.
Yeah, that safety piece, it's not just bolted on at the end. It's absolutely foundational. I mean, industrial radiography, using X-rays or gamma rays to check inside stuff, it relies entirely on us accepting some really radical shifts in how we even thought about the physical world. So this story, it's not just pure science. It's also about, well, regulation, trying desperately to keep up with this new power we unleashed. We'll be looking at these two threads that you just can't pull apart. The physics, like how the beams actually work, and then the safety standards that had to emerge to handle the risks.
If you're an industrial radiographer preparing for your state radiation safety exam, the Radiation Safety Test Prep app is built just for you. Available now on the Apple App Store, this powerful study tool helps you learn smarter, not harder, with 2 study modes designed to fit your pace and experience. In study mode, review detailed explanations after each question to build a solid understanding of radiation principles and safety practices. Switch to test mode to simulate real exam conditions, test your timing, and measure your readiness before test day. You can even tailor your practice by focusing on gamma, X-ray, or both, making your study sessions as targeted and efficient as possible. Stay safe, study smart, and pass with confidence.
The inherent risks that come with that kind of energy.
Okay, so to really get X-rays, we have to rewind, like way back. What is stuff? What's it made of? Let's jump back, 2,000 years plus, to the ancient Greeks. For centuries, there was this huge debate about, does matter, like this continuous goo you can just keep cutting forever, or is it made of tiny fundamental bits you can't cut?
Exactly. And that second idea, the indivisible block, that gave us the word atomos, Greek, right? Or to mean not. Tomos meaning to cut. The atom, the smallest possible piece.
Right.
But here's the crazy part. That idea, the correct idea basically, it got ignored for something like 2,000 years until, the Enlightenment really got going. The main model in the West came from Aristotle.
Ah, the classic 4 elements, earth, air, fire, water.
That's the one. And you can kind of see why it stuck around, right? It feels intuitive. You burn wood, you see fire, smoke, that's air, moisture, comes out water, and you're left with ash earth. It seems to fit. It really took until the 17th 18th centuries, with chemists doing actual rigorous measurable experiments to finally force the scientific world to admit, okay, no, it's distinct elements, and these elements combine as atoms. That's the real building block of everything. So accepting the atom was step one. But then came the next puzzle, maybe even weirder, what's inside the atom. The idea that you could crack open this supposedly indivisible thing, that must have seemed wild.
Oh, absolutely. Almost like heresy for a while there. The first decent conceptual model really came about in 1907. Sir John Thomson's plum pudding model.
You like the plum pudding? Always sounded kind of tasty. Yeah. Imagine like a ball of positive pudding, positive electricity, and then scattered inside it are these little negative electrons like plums or currents. The whole thing balances out. Zero net charge. It was revolutionary because, hey, subatomic particles. But, science moves fast. By the 1910s, other experiments, especially Rutherford shooting particles at gold foil, showed something different. The atom was mostly empty space, with this tiny, dense, positive thing right in the middle, the nucleus.
Okay, so that leads us towards the model we kind of use now to think about energy and atoms interacting. The electron structure is key here, right? Because that structure is basically where X-rays come from, totally key. And it's not random. Electrons aren't just buzzing around anywhere. Quantum mechanics dictates this really organized structure. Electrons live in distinct shells. You might remember KLMN shells from school. And within those, Subshells, SPD.
Each shell is a specific energy level. And the crucial rule is electrons always fill the lowest energy levels first. They pack into the K shell, then the L, and so on. They're bound to that positive nucleus, and the closer they are, like in K shell, the more energy it takes to kick them out.
And this gets into some really deep physics, doesn't it? This whole particle wave thing.
It really does, the dual nature of matter. An electron, yeah, we often picture it like a tiny ball orbiting, but it also behaves like a wave. Its position and energy are described by mathematical wave functions. It's weird, but fundamental. And this duality applies to everything down at that scale. It helps explain how a photon, which is just pure energy, an X-ray photon, can interact with and knock out an electron, which clearly has mass. Particle meets wave, wave meets particle. It's mind-bending stuff.
Okay, so if the electrons are normally in this neat, ordered structure, what happens when things get disrupted, when energy changes? That's where these penetrating rays are born. Let's first talk about what makes an atom unstable to begin with. Radioactivity.
Right, so now we shift focus from the electron clouds buzzing around the outside, deeper into the core, the nucleus itself. Some atoms, radioisotopes, are just naturally unstable. Usually it's because the number of neutrons compared to protons creates this energy imbalance. To get stable, the nucleus has to basically rearrange itself. It undergoes nuclear disintegration, or what we call radioactive decay. And in doing that, it has to shed that excess energy. Sometimes that's particles flying out, sometimes it's high-energy photons, and often the atom actually changes into a different element because its atomic number changes. Okay, now for a really critical distinction, especially for the radiography we're talking about, gamma rays versus X-rays. Physics-wise, they're like twins, right?
Right.
But where they come from is totally different.
Exactly. They're both electromagnetic rays, like light, but way, way higher energy. Highly penetrating. Non-ionizing isn't quite right. They are ionizing, but yeah, same family. The difference is parentage, like you said. Gamma rays, they are born inside the nucleus during that radioactive decay we just talked about.
They represent the energy released when that unstable nucleus settles down into a more stable state. X-rays, on the other hand, they come from outside the nucleus. They happen because of changes in the electron orbits or when electrons get slammed to a stop.
Right, so if something, like another particle or a photon, hits an atom hard enough and knocks an electron out of an inner shell, let's say the K shell, the closest one in,
Yeah.
then there's a vacancy, right? An empty spot. And nature doesn't like that. So an electron from a higher shell, like L or M, immediately drops down to fill that hole.
Precisely. And since that L shell electron was at a higher energy level than the K shell spot it just filled, it has to get rid of that extra energy somehow.
And that's the X-ray.
That's an X-ray. Specifically, it's a characteristic X-ray. Pops out as a photon with a very specific energy, determined by the difference between those two shells. And that energy difference is unique. It's characteristic of that specific element, like a fingerprint. But characteristic X-rays, while important, aren't the whole story for making X-rays, especially in machines. There's another process, arguably even more important for radiography generators, Bremsstrahlung, IS the German. Breaking radiation. That sounds important. That's the main event inside an X-ray tube, isn't it? Tell us why that's so critical. It really is the workhorse. Bremsstrahlung, breaking radiation. It happens when you shoot high-speed charged particles, usually electrons fired across an X-ray tube past the nucleus of an atom in the target material. That nucleus is packed with positive protons, right? So it has a strong positive charge. As the speeding negative electron flies past, that positive charge yanks on it, causes it to swerve, change direction, and slow down. It breaks. And just like hitting the brakes in your car converts motion energy into heat in the brake pads, this electron decelerating has to dump its lost kinetic energy. It does that by radiating an X-ray photon.
Okay, but unlike the characteristic X-rays with their specific energies, Bremsstrahlung is different.
Totally different outcome. The amount of braking, the amount of energy lost, it varies wildly. An electron might just get a slight nudge from the nucleus, lose a little energy, and produce a low-energy X-ray. Another electron might score a near-direct hit, slam on the brakes hard, lose almost all its energy, and create a really high-energy X-ray photon. Up to the maximum energy determined by how fast it was going in the first place, which is set by the tube voltage. So because you get this whole range of interactions from glancing blows to near head-on collisions, Bremsstrahlung doesn't produce sharp energy peaks like characteristic X-rays. It produces a continuous spectrum of X-ray energies, a smooth distribution from low to high.
And you mentioned something in the source material connecting this back to the target material itself. The fraction of energy that actually becomes X-rays depends on the atomic number Z. Why is Z so important here?
It all comes down to how strong that positive charge in the nucleus is. The higher the atomic number Z, the more protons are crammed in there. More protons mean a stronger positive electrostatic field around that nucleus. A stronger field pulls harder on those incoming electrons. It causes bigger deflection, more braking, more deceleration. And a more severely decelerated electron radiates more of its energy as X-rays. So higher Z means better X-ray production efficiency.
Which is why they use things like tungsten in X-ray tubes.
Exactly. Tungsten, Z is 74. Sometimes they even use gold, Z is 79. Really heavy elements. If you tried to make an X-ray tube target out of something light, like aluminum, Z equals 13, you'd get hardly any X-rays. Almost all the energy from the electrons hitting it would just turn into heat, which is already a big problem, even with tungsten, #C, the discovery and early industrial adoption.
Okay, understanding that physics, it almost makes the discovery seem like it was bound to happen, even though it was totally by chance.
Let's jump to 1895, Wilhelm Röntgen. Yeah, the exact date they pinpoint is Friday, November 8th, 1895. Röntgen's in his lab at the University of Würzburg. He's messing around with cathode rays, these beams of electrons inside evacuated glass tubes. Standard stuff at the time. But he notices something weird. Across the room, there's a screen coated with a phosphorescent material, and it's glowing. Which is odd because the tube he's working with is covered in thick black cardboard. No visible light could be getting out.
So he realizes he's made some kind of invisible ray.
Exactly. Something new, something unseen that could actually pass through solid stuff like cardboard. He didn't know what it was, so he called them X-rays. X for unknown.
And the reaction wasn't just, oh, interesting science. It exploded, right, culturally, too.
Oh, it was absolutely sensational. Within weeks, by early January 1896, it was global news. The public was instantly fascinated, mainly because of that see-through property. Röntgen himself made that famous image of his wife's hand.
Yeah, the one showing her bones and her wedding ring.
Yeah.
Spooky.
Totally spooky back then. It was the first time anyone had seen inside a living human body without cutting it open. Medicine was changed overnight. Bone fractures, foreign objects, suddenly visible. But the press, yeah, they ran wild with it. Not just medical uses. There was actual genuine panic in some circles. People worried about privacy. Could these rays see through walls? Through clothes? There were serious articles suggesting women needed to buy X-ray-proof underwear for modesty. It shows just how disruptive it felt.
That's wild. X-ray-proof underwear. But okay, amidst all that social buzz and the medical revolution, the industrial folks didn't miss a beat either, did they? Even if it was quieter.
Nope, engineers saw the potential immediately. While hospitals were setting up X-ray rooms, factories were thinking, hey, we can use this to check quality before something breaks. Very early on, things like artillery shell casings were being radiographed. They need to know, is the explosive filling packed in evenly? Are there hidden cracks or voids in the metal that could make the shell blow up in the cannon?
So it shifted from just testing if it worked, like, did the shell fire okay, to checking if the material itself was sound beforehand.
Precisely. That's the birth of real non-destructive testing, or NDT as we know it, finding flaws without destroying the part.
And that immediate industrial need must have pushed them to improve the X-ray source itself, right? To make it more controllable than Röntgen's initial setup.
Absolutely. Control was everything. You needed to control how much radiation came out, the intensity, and how penetrating it was, the energy. The standard X-ray tube design, which honestly hasn't changed that much in principle, emerged pretty quickly. It's a vacuum tube, basically. You've got three main bits. A heated filament, that's the cathode or electron source, a focusing cup to aim those electrons, and a target, the anode, usually made of that high Z material like tungsten. The filament gets heated by its own little circuit, a low-voltage one. How hot you make it determines how many electrons boil off. More electrons mean more X-rays per second. That's the tube current, measured in milliamperes. Higher MA means shorter exposure times.
Okay, so filament heat controls MA, which controls the X-ray intensity. What about the power, the penetration? That's the kV, right?
That's the kV, the kilovoltage. That's the huge voltage difference you put between the filament cathode and the target anode. This voltage difference acts like a giant accelerator, pulling the electrons across the vacuum gap at incredible speed. The higher the kV, the faster the electrons hit the target. Faster electrons have more energy to lose when they break or Bremsstrahlung. So higher kV means the resulting X-ray spectrum reaches higher maximum energies. Higher energy means more penetrating power. You need high kV to get through thick steel, for example.
But you mentioned heat before. That's the big downside.
Massive downside. Remember, only about 1% of the energy for those electrons actually becomes X-rays. The other 99% just turns into heat, right there at the tiny spot on the target where the electrons hit. That's why tungsten is critical. Its melting point is insanely high, over 3 to 400 Celsius. And for really tough industrial jobs, inspecting super thick or dense parts, they had to invent specialized tubes.
Like what? Give us some examples.
Okay, two big ones come to mind. First, the rod anode tube. Imagine you need to inspect the inside of a long, skinny pipe, or maybe a boiler tube. A normal X-ray tube is too big and clunky to fit inside. The rod anode tube is designed so the anode, the target part, is on the end of a long, thin extension rod. You can poke this rod right down the pipe, positioning the X-ray source perfectly in the center. Great for getting the right geometry when you have internal access, but it's tight.
Okay, that makes sense for pipes. What's the other one?
The other is the 360-degree panoramic tube. Think about welding a big pipeline together. You have that weld going all the way around the circumference. You don't want to take like 20 different X-ray shots from different angles. That takes forever. The panoramic tube is clever. It positions the tungsten target so it's perpendicular, edge-on, to the electron beam. Instead of the X-rays coming out in a cone, they spray out in a full 360-degree circle, like a donut.
Ah, so you stick the tube inside the pipe, wrap the film around the outside.
And bang! One shot gets the entire circumferential weld. Super efficient. Huge time and cost saver in pipeline construction and repair.
These specialized tools really let engineers go way beyond just seeing shadows. This is where NDT really formalizes itself. How does radiography fit into that bigger NDT picture?
Well, NDT, non-destructive testing, the name says it all, right? It's about checking a material or component for problems without damaging it. So you're not proof testing it destructively. You're asking, is there something wrong inside? Radiography's specific job is looking for things inside the volume of the material, things like porosity, little gas bubbles trapped in a weld, or slag inclusions, bits of non-metallic stuff caught in the metal, or internal cracks that don't reach the surface. Because it sees through the whole thickness, radiography is classified as a volumetric NDT method. It checks the volume, not just the surface.
But early on, it was still basically just a shadow on film. How did they get better at seeing fine details and actually understanding the 3D structure from that 2D image?
Well, a big leap came in the early 50s, 1951, with Coslet and Nixon. They figured out geometric magnification using X-rays, creating the X-ray shadow microscope. See, in medical X-rays, usually you put the body part right up against the film or detector. You get pretty much a 1-to-1 size image. If you try to magnify it by moving the patient away from the detector, the image gets blurry because the X-ray source isn't a perfect point. It has a small size, the focal spot.
Okay. But in industry, especially if you're looking at tiny components or trying to analyze exactly how something failed, you want magnification to see the details. Geometric magnification works by doing the opposite. You move the object really close to the X-ray source, specifically a source with a very, very tiny focal spot, a microfocus tube. You keep the detector further back. The magnification you get is just a simple ratio. The distance from the source to the detector divided by the distance from the source to the object. So source to detector over source to object. And the tiny focal spot keeps it sharp.
It's exactly. With a microfocus tube, you can get significant magnification without completely blurring out the image. This lets you inspect things with features down in the micrometer range, sometimes even smaller. It turned radiography from just finding big flaws into a high-resolution investigation tool. Hashtag HLIBD, industrial sources, detection, and the safety imperative. Now, that magnification trick really relies on having a controllable X-ray machine source. But a huge amount of industrial radiography uses the other kind of source, radioisotopes, gamma rays. These are like the workhorses out in the field, right? Because they don't need plugging in. That's their huge advantage, portability and independence from power. They just sit there and decay, constantly emitting gamma rays. Perfect for field work, construction sites, pipelines out in the middle of nowhere. The two main players in industry are Iridium-192 and Cobalt-60, and comparing them really highlights the trade-offs you deal with when using radioactive sources.
Okay, break those down for us. Iridium first, right? Iridium-192, often written as IR-192. Its big characteristic is a relatively short half-life, only about 75 days. Wait, half-life. Remind us what that means exactly.
Half-life, T, is the time it takes for half of the radioactive atoms in a sample to decay. So for Iridium-192, if you start with, say, 100 curies of activity today.
A curie being the unit of activity.
Right, a measure of how many atoms are decaying per second. So 100 curies today, in 75 days, you'll only have 50 curies left. In another 75 days, 150 total, you'll have half of that, 25 curies, then 12.5, and so on. It decays exponentially, not linearly.
So 75 days isn't very long in industrial terms. No, it means an iridium source gets noticeably weaker pretty fast. You have to replace the source every few months, which is a significant operating cost and logistical hassle. Its energy is suitable for, say, steel up to maybe 50 millimeters, a couple of inches thick, and its dose rate is Well, significant but manageable. About 5.2 Roentgen per hour at 1 foot away from a 1 Curie source. Okay, so relatively short-lived, moderate energy. What about cobalt-60? Cobalt-60, Co-60 is a whole different ballgame. Its half-life is much longer, 5.27 years. So a cobalt source stays useful for a long time, which is good economically, but the trade-off is energy and intensity. Cobalt-60 emits two very high-energy gamma rays, 1.17 and 1.33 million electron volts. Much punchier than iridium. And its dose rate is way higher, about 14.0 Roentgen per hour at 1 foot from a 1 Curie source. Whoa, nearly 3 times the dose rate of iridium-192 and much higher energy photons. What does that mean practically for someone working with it?
That high energy is the kicker.
Yeah.
Higher MEV gamma rays are much harder to stop. They penetrate more easily, which means a cobalt-60 source needs a lot more shielding, thicker, heavier lead or depleted uranium in its storage container, the camera, to keep the radiation exposure safe for the operator and the public. So while cobalt-60 is essential for looking through really thick stuff, heavy steel sections, big castings, dense materials where iridium just wouldn't penetrate, handling that much heavier, bulkier shielded camera is a major operational challenge. It affects transport, setup, everything. It's a bigger safety consideration day to day.
And that half-life concept, the nonlinear decay, that's critical for tracking how strong a source still is, right? You can't just assume it loses the same amount of power each month.
Absolutely critical. You need decay charts or software to know the current activity of your specific source on any given day. Exposure times have to be adjusted constantly as the source weakens, otherwise your radiographs won't come out right. And safety calculations like boundary distances also depend on knowing the current activity accurately. It never truly goes to zero, just gets weaker and weaker over many, many half-lives. Radiation safety is forever. Okay, so whether it's X-rays from a machine or gamma rays from an isotope, the number one job for the radiographer is controlling their exposure and the exposure of others. Let's get down to the brass tacks. The 3 golden rules of radiation protection. Simple concepts, but they save lives. Time, distance, and shielding. Time is the most straightforward. Your total dose is directly proportional to how long you're exposed. Exposure E equals source activity, M in Curies, let's say for gamma times time T. Gamma exposures are often even planned in Curie hours. Simple math. Spend half the time of the radiation field, you get half the dose. So efficiency, planning your work meticulously before the source comes out, it's not just about productivity, it's a safety function.
Makes sense. Less time, less dose. What about distance? You said that's maybe the most powerful tool. By far, thanks to a beautiful, simple law of physics. The inverse square law. Ah, sounds important. How does it work?
It states that the intensity of radiation, I squared, decreases with the square of the distance d from a point source.
Right.
The relationship is $d12 equals I2 d22. Think about it. If you double your distance from the source, say, go from 1 meter away to 2 meters away, the radiation intensity doesn't just get cut in half, it drops to 1/4 because 2 squared is 4.
Oh.
Triple the distance. The intensity drops to 1/9. 3 squared is 9.
Wow. Okay. So a little extra distance makes a huge difference.
A huge difference. This is why radiographers use handling kongs, remote cranks, guide tubes, anything to maximize their distance from the source while working. Even moving just one step further back during setup can dramatically reduce your dose. And it's why setting up a controlled boundary, a rope barrier, around the work area is absolutely non-negotiable. Someone wandering just a few feet closer than they should be inside that boundary, their dose rate shoots up exponentially. The inverse square law is your best friend for safety.
Okay. Time, distance. What's the third pillar? Shielding.
Shielding. This is about putting some kind of dense material between you and the source to absorb the radiation. Lead is the classic example, especially for X-rays because it's very dense and has a high Z number. Steel, concrete, even water can be used. For X-ray machines, the shielding is often built right into the tube housing. For isotopes, the source lives inside that heavily shielded camera or projector we mentioned, usually made of depleted uranium or tungsten, which are even denser than lead. The shielding material absorbs or scatters the radiation photons, reducing the intensity that gets through.
And the thicker the shield, the better.
Generally, yes, but it also depends heavily on the energy of the radiation. Those high-energy cobalt-60 gammas need much thicker shielding than lower-energy iridium gammas, or typical diagnostic X-rays, to achieve the same dose reduction. Shielding is often considered the last line of defense, though. Optimizing time and maximizing distance are usually the first things you try to do. They're often cheaper and easier to implement than adding tons of lead.
We'd also like to recognize Skaggs Media LLC as the creative force behind today's deep dive. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skagsmedia.com. Now, it's really important for you listeners to get this. The safety rules we follow today, these strict dose limits and procedures, they weren't just plucked out of thin air. They evolved, often painfully, especially after World War II.
The whole atomic age, the bomb development, the nuclear reactors,
Mhm.
it suddenly created a whole bunch of new artificial radioisotopes that didn't exist naturally. And the potential for exposing large populations, not just lab workers, became a massive concern.
And this forced a fundamental rethink about radiation risk, didn't it? Before the war, they had this idea of a tolerance dose. Like, a little bit was probably okay.
Exactly. The prevailing thought was, yeah, there's probably some threshold. Below this level of exposure, no harm done. But then came the post-war research, especially studies on genetics, looking at fruit flies and mice exposed to radiation, and those studies were disturbing. They showed that reproductive cells, the ones passing traits to offspring, seemed susceptible to damage even at very low doses. There didn't seem to be a safe threshold for genetic mutations.
Yeah.
Damage looked like it might be cumulative, proportional to dose, however small.
That must have sent shockwaves through the radiation protection community.
It completely shattered the tolerance dose concept. The main body in the U.S. setting standards, the NCRP National Council on Radiation Protection and Measurements, they acted pretty decisively. In 1946, they basically said, okay, tolerance dose is out. They replaced it with a new concept, the maximum permissible dose. And crucially, they slashed the recommended limits for people working with radiation.
How big a cut are we talking about?
It was dramatic. Before 46, the guideline was around 0.1 Roentgen per day. The new limit became 0.3 Roentgen per week, based on a 6-day work week then. If you do the math, the annual limit effectively dropped from around 30 Roentgen down to 15 Roentgen, basically cut in half, almost overnight.
Wow, that must have caused chaos for industries using radiation, suddenly needing much better shielding, stricter procedures, huge operational impact. But here's the really critical point, something everyone working in this field should understand about the history. That reduction, that halving of the dose limit, it wasn't because they were seeing widespread harmful effects in workers at the old 30 Roentgen limit. They weren't. It was done out of prudence. The thinking was driven by the genetic risk data, the lack of a clear threshold, and a new philosophy. If we can practically reduce the dose further without completely crippling the necessary uses of radiation, then we should. It was a proactive, cautious step. And that cautious, proactive approach, that's what led to the guiding principle we use today, exactly. It evolved into the core philosophy of modern radiation safety, ALARA, as low as reasonably achievable, ALARO. You hear it all the time in NDT. It's not just a target number then.
No, it's much more than just staying below the legal dose limit. LRI is an active process. It means constantly looking for ways to reduce exposure, even if you're already well below the limits, using better shielding, improving procedures, using faster detectors, maximizing distance, anything reasonable to minimize the dose. The underlying assumption is that any dose of radiation carries some tiny theoretical risk of long-term effects, like cancer or genetic damage. So the goal isn't just compliance, it's minimizing that potential harm across the whole population of exposed workers in the public as much as is practically possible.
Okay, so LRI drives the practical safety culture. To understand the risks we're minimizing, let's talk about the biological effects. What happens when radiation actually interacts with the body?
Broadly, we split the effects into two categories. First, somatic effects. These are effects that happen to the person who is actually exposed, the irradiated individual. This ranges from immediate acute effects if the dose is high enough, like radiation sickness, burns, hair loss, all the way to delayed effects that might show up years later, like cancer.
Okay, somatic is harm to the self. What's the other category?
The other is hereditary effects, sometimes called genetic effects. This is damage to the reproductive cells, sperm, or eggs. This damage doesn't harm the exposed person directly, but it can potentially cause mutations that are passed down to their children or even later generations. This was the big concern driving that post-1946 dose limit reduction.
What about those immediate acute effects? Are there benchmarks for how much radiation causes serious problems quickly?
Yeah, there are some rough benchmarks, usually based on a large, single, whole-body exposure. If someone receives more than about 2 grays, that's the modern unit, roughly equal to 200 rads acutely, they'll likely experience some symptoms of radiation sickness, nausea, vomiting, fatigue. Get up to around 4 gray or 400 rads, and you're in the territory of the LD50-60. That's the lethal dose for 50% of the population within 60 days if they don't receive intensive medical care. Survival is possible, but requires significant treatment. Once you get exposures exceeding about 7 gray or 700 rads, survival becomes very unlikely, even with the best medical intervention. That's often considered the LD100 range.
Yeah.
These are huge doses. Thankfully, very rare outside of major accidents.
And you mentioned sensitivity earlier, the developing embryo.
Extremely sensitive, especially in the first trimester, really weeks 2 through 8 after conception, when organs are rapidly forming. Doses above about 0.3 gray or 30 rads during that critical window can cause teratogenesis, severe birth defects, physical abnormalities, potential mental retardation. This extreme sensitivity is why the regulations for pregnant workers are so much stricter. Their dose limit is typically kept to about 1/10 of the limit for other radiation workers throughout the entire pregnancy. Protecting the fetus is paramount.
Okay, those acute numbers are pretty stark. But putting it in perspective, how risky is industrial radiography day to day when done correctly following LOR and regulations?
Statistically, when procedures are followed, it's actually quite safe compared to many other industrial jobs. The source material we looked at cited data suggesting that the average industrial worker across all industries faces something like 20 times the risk of developing cancer from exposure to chemical substances on the job than the average industrial radiographer faces from their occupational radiation exposure.
20 times higher risk from chemicals than radiation for the average worker versus the radiographer. That's surprising.
It puts things in perspective. The potential hazard from radiation is high, yes, but the engineering controls, the shielding, the procedures, the regulations, the training, the whole safety framework built around it is incredibly effective at managing that hazard down to very low levels of actual risk for the people doing the job properly.
So, if the system is so robust, why do accidents still happen? It sounds like it's rarely the equipment failing.
Overwhelmingly, accidents are procedural failures, human error, not the source randomly leaking or the shielding failing. The sources point to 3 main culprits, the things that repeatedly cause significant exposure incidents. Every learner needs these burned into their brain.
Okay, what are the big 3?
Failure to fully retract the source, not winding the radioactive source all the way back into its shielded container, the camera, after the shot is done, leaving it exposed in the guide tube.
Omitting or performing an inadequate radiation survey. Not using your survey meter correctly or at all to verify that the source is actually back in the shield and the radiation levels have dropped to safe background levels before approaching the setup or removing barriers, assuming it's safe without checking. And number 3, failure to properly lock or secure the source, leaving the camera unlocked when unattended, or not securing the entire device properly during transport or storage, allowing unauthorized access or potential theft.
So it really boils down to complacency or cutting corners on basic procedures.
Pretty much. The equipment is designed with multiple safety features, but they rely on the operator following such rigorously every single time. Checklist discipline. Survey, survey, survey. Lock it up. Those are the keys to preventing almost all radiography accidents. Hashtag FEATTAG, e-detection, and advanced imaging techniques.
Right. And doing those surveys, adhering to ALA-RI, it all depends on being able to actually measure the radiation accurately. Which brings us to the detectors themselves. How do we see this invisible energy? Let's start with the classic, the one everyone recognizes the sound of, the Geiger counter. How does that taken box actually work? Okay, the Geiger counter, or GM counter, is a type of gas-filled detector. The basic idea is simple. You have a tube filled with specific gas, usually an inert gas like argon. There's a central wire running down the middle, the anode, held at a high positive voltage relative to the outer tube wall, the cathode. When a radiation particle or photon, say a beta particle or a gamma ray, flies into the tube, it bumps into gas molecules and knocks electrons off them. It ionizes the gas. Now you have free electrons and positive gas ions.
And the electrons head for the positive wire.
Exactly. That high voltage yanks those freed electrons towards the central anode wire. As they accelerate towards it, in a GM tube, the voltage is set so high that these electrons gain enough energy to smash into other gas molecules and knock more electrons off. This creates a cascade, an avalanche of electrons hitting the wire from just one initial ionization event. It's called gas amplification. This avalanche creates a relatively large, easily detectable electrical pulse for each initial radiation particle that entered the tube. That pulse gets converted into the audible click, or a reading, in counts per minute CPM.
So that amplification makes it super sensitive.
Incredibly sensitive. Great for detecting very low levels of radiation, finding contamination, or confirming if a source is out when it shouldn't be. The downside is, because of that huge avalanche, every pulse is the same size, regardless of whether the initial particle was high energy or low energy. So a GM counter can't easily tell you what kind of radiation it is or its energy, and they can get overwhelmed, saturated in very high radiation fields.
Okay, sensitive for detection, but not great for measuring high doses or energy. What about the badges people wear? Film used to be common, but now it's mostly TLDs.
Right, thermoluminescent dosimeters, TLDs. They largely replaced film badges for personal monitoring because they're more accurate over a wider dose range, less affected by environment, and reusable. TLDs use special crystalline materials, often lithium fluoride chips. When radiation hits the crystal, it deposits energy, which excites electrons within the crystal lattice. Some of these excited electrons get stuck in defects or traps in the crystal structure, kind of like storing the energy. They stay trapped there at room temperature.
So the badge just sits there, accumulating trapped electrons based on the dose received.
Exactly. Then, to read the dose, you take the TLD chip back to the lab and heat it up under controlled conditions. That's the thermo part. The heat gives the trapped electrons enough energy to escape the traps and fall back down to their normal energy levels. As they fall back down, they release that stored energy in the form of visible light, that's the luminescence part. A sensitive device called a photomultiplier tube measures the total amount of light emitted. And that amount of light is directly proportional to the radiation dose the crystal originally absorbed. So you get a precise, quantitative reading of the worker's exposure.
Clever. Storing energy, releasing it as light later. What's the third main type of detector you mentioned? Scintillation. Sounds flashy.
Huh? Yeah, scintillation detectors do involve flashes of light. They are incredibly versatile and widely used, especially when you need to know the energy of the radiation, not just its presence or total dose. They work using materials called scintillators. These can be certain types of crystals like sodium iodide, plastics, or even special liquids. When radiation interacts with the scintillator material, it excites the molecules, and they quickly de-excite by emitting tiny, brief flashes of light scintillations. In a liquid scintillation counter, for example, the radioactive sample is mixed with a cocktail containing a solvent and a fluorescent chemical called a fluor. The radiation energy excites the solvent, which transfers the energy to the fluor, which then emits the light flash.
And the key difference from a GM counter is?
The key is that the intensity of each light flash, the number of photons produced, is directly proportional to the energy deposited by the initial radiation particle, or photon. A high-energy beta particle will create a brighter flash than a low-energy one. So by measuring the brightness of each flash with the photomultiplier tube, you can not only count how many radiation events are happening, but also determine their energy distribution. This is crucial for identifying specific isotopes or doing complex analysis.
But the source material mentioned a problem with scintillation counting, something called quench. What's that about?
Quench. Yes, that's a major practical challenge, especially in liquid scintillation counting when you're analyzing real-world samples like biological tissues or environmental swabs. Quench refers to anything that reduces the efficiency of the light production or detection process, leading to an artificially low reading. For instance, if your sample is colored like from blood or plant chlorophyll, that color can absorb some of the scintillation light before it reaches the detector. Or certain chemicals in the sample might interfere with the energy transfer process itself. This means the measured light intensity isn't accurately reflecting the original radiation energy. Labs using scintillation counters have to employ various sophisticated methods to measure the amount of quench happening in each sample and then mathematically correct for it to get accurate results. It's a constant battle in low-level counting.
Okay, so we can detect and measure radiation precisely. Let's shift back to the imaging side, but now looking at the really advanced stuff, moving beyond that simple 2D shadow from Röntgen's time. Computed tomography, CT scanning, that's a huge leap, right?
Oh, monumental. CT is arguably one of the biggest advances in volumetric imaging, both medically and industrially. Think about traditional radiography again, it's a projection. All the information from the front to the back of the object is compressed into one 2D shadowgram. It's like trying to understand a whole building just by looking at its silhouette. CT does something radically different. It takes hundreds, sometimes thousands, of individual X-ray projection images from many different angles all around the object. Then, powerful computers take all that projection data and use complex mathematical algorithms, reconstruction algorithms, to calculate what the internal structure must look like, slice by slice.
So it builds up a 3D picture from all those 2D views.
Exactly. It generates a stack of cross-sectional images, like virtual slices through the object. And crucially, these aren't just pictures. They are quantitative maps of the X-ray attenuation coefficient, which relates directly to material density at every point voxel within that slice.
And the payoff in terms of sensitivity, how much better is it than a standard X-ray image?
The difference is staggering. Industrial CT systems can typically resolve differences in density that are 10 to 100 times smaller than what you could ever hope to see on a conventional 2D radiograph. Tiny variations in material density, subtle flaws, slight changes in composition, things that would be completely invisible on film can often be clearly detected and measured with CT.
That level of detail must open up completely new applications in industry. Absolutely. It's transformative for things like failure analysis pinpointing the exact origin of a microscopic crack inside a complex casting or a turbine blade. Product development, non-destructively inspecting and validating prototype parts, especially complex ones made by, say, 3D printing, to ensure they match the design intent perfectly.
It's used for reverse engineering scanning an existing part to create a highly accurate digital CAD model, and for characterizing really complex or thick objects like multi-material assemblies, dense geological samples, or even archaeological artifacts, where traditional radiography just gives you a confusing jumble. CT lets you digitally dissect it layer by layer.
Okay, CT is amazing when you can get signals through the part from all angles. But what if you physically can't? Like, you need to inspect something, but you can only get to one side of it. That happens a lot in maintenance, right? Aircraft structures, maybe?
That's a classic problem, and the solution is usually backscatter radiography. Imagine you need to check the integrity of a large aircraft bulkhead, or maybe look for corrosion under the skin of a wing. You can't put an X-ray source inside the fuel tank and a detector on the outside easily. So, in backscatter, you use the radiation that scatters back towards the source. You rely on the Compton scatter effect. When the primary X-ray photons hit the material, some of them interact with electrons, lose a bit of energy, and scatter off in various directions, including backwards. You place your detector on the same side as the X-ray source, shielded from the direct beam, positioned just right to catch those backscattered photons.
But how does scattered radiation give you a useful image? Isn't it just noise, usually?
Normally, yes, scatter degrades image quality in transmission radiography, but here, the amount of backscatter depends on the density and composition of the material right near the surface the beam is hitting. So if you scan the beam across the surface, areas with different densities or hidden voids underneath will scatter back different amounts of radiation. For instance, going back to those artillery shells, you could use backscatter to check if the explosive filler comes right up to the casing. Where there's a dense filler, you get one level of backscatter. If there's a hidden air gap, a void, the backscatter signal changes. It's great for detecting near-surface flaws or material changes when you only have single-sided access. Fascinating. Using the scatter instead of fighting it. Okay, one more specialty area. Flash radiography. This sounds like high-speed photography, but with X-rays, that's exactly what it is. Flash radiography, or cineradiography, is all about capturing images of incredibly fast events, things that happen in microseconds or even nanoseconds. Think ballistics, a bullet penetrating armor, or studying explosions, shock waves propagating through materials, the dynamics of fuel injection sprays. Because the event itself is over so quickly, your X-ray exposure has to be equally short, otherwise you just get a motion blur. We're talking X-ray pulses lasting less than a microsecond, a millionth of a second, and for really extreme physics experiments, down into the sub-nanosecond billionths of a second.
Hold on, generating a powerful X-ray burst that lasts less than a billionth of a second. The engineering behind that must be insane. We're talking maybe 600,000 volts, maybe 10,000 amps of current switched on and off in nanoseconds.
It is absolutely bleeding-edge pulse power engineering. You need specialized X-ray tubes designed to handle enormous instantaneous power and incredibly sophisticated high-voltage switching systems, things like Marx generators, Bloom lanes capable of delivering that massive electrical pulse with picosecond precision. It really pushes the limits of electrical engineering just to make the imaging possible for those fleeting moments.
Okay, and wrapping up the tech side, the shift from film to digital detectors, things like CCDs, the sensors in digital cameras, or linear diode arrays. What's the big win there for analysis?
The biggest advantage, fundamentally, is dynamic range. Film has limitations. If the exposure is too low, it's clear, too high, it's black. The range of useful densities it can capture simultaneously is quite narrow. Digital detectors like CCDs or flat panels using amorphous silicon or selenium, they're different. They can accurately measure a much wider range of X-ray intensities, hitting them in a single shot. Modern industrial digital detectors often operate with 16 bits of data depth per pixel.
16 bits. What does that mean in practical terms for someone looking at the image?
16 bits means that for each pixel, the detector can distinguish between 2 to the power of 16, which is 65,536, different levels of gray or intensity. This gives you a huge dynamic range, maybe 64,000 to 1 or even more. Why does that matter? Imagine inspecting a casting that has really thick sections right next to very thin sections. With film, you'd have to choose expose correctly for the thick part and completely black out the thin part, or expose for the thin part and get nothing through the thick part. You might need multiple exposures at different settings. With a high dynamic range digital detector, you can often capture useful image information in both the very thick and the very thin areas in a single exposure. The raw data contains all that information. Then, using software, you can adjust the contrast and brightness, window, and level on the display to examine details in any part of that wide range. It makes analysis much faster and more powerful.
Is there still a limit, though? What determines how small a detail you can see with digital?
Yeah, the fundamental limit on spatial resolution, how small a thing you can distinguish, ultimately comes down to the detector itself. Specifically, the size of the individual detector elements, the pixels, and the spacing between them, the pixel pitch. You can't reliably resolve features that are smaller than the pixel size. So smaller pixels generally mean potentially higher resolution, although other factors like scatter and focal spot size also play a role. #tag F, final takeaways and continuing education.
Wow. Okay, we've really covered some ground, from ancient Greeks arguing about atoms through Thomson's plum pudding model, which was, well, kind of wrong, but a step.
The necessary step.
Right. To Röntgen stumbling onto X-rays, the rapid industrial use, Cobalt-60, LRLA, CT, scans mapping densities, all the way to digital systems giving us, 65,000 shades of gray? It's been quite the evolution.
It really has. And the core theme, the synthesis, is this duality we talked about. Industrial radiography is this incredibly powerful tool, a volumetric NDT method, giving us this amazing window into the internal health of materials, essential for safety and quality in so many fields. But that power comes bundled with significant potential hazard. The high energies involved mean the safety aspect isn't optional, it's integral. That prudent decision back in 1946, moving away from tolerance to maximum permissible dose, and the whole philosophy of Al-Ra that grew from it, that's what allows us to use this technology responsibly. The physics lets us see inside the material. The safety framework protects the person running the machine. They have to go hand in hand.
And that increasing power, especially with things like high-resolution CT, it changes the game for what we even consider a flaw, doesn't it?
Absolutely. That's the perfect thought to leave our listeners with. We've gone so far beyond just looking for big, obvious defects as gross black shadows on film. Now we're creating these incredibly detailed quantitative 3D maps of density variations. We can potentially detect tiny imperfections, microporosity, subtle density shifts related to material processing, things that are maybe 10 or 100 times smaller than what older standards were based on. There's the provocative question for you, especially if you're working in or learning about NDT and material science, is this. As our imaging technology continues to get better and better, maybe we'll be routinely seeing features down at the nanoscale soon. How do our acceptance standards need to evolve? The codes and specifications that define what's okay and what's not okay in a critical component like a pressure vessel or an aircraft part. If our tools allow us to see everything down to the grain structure, does that mean we have to reject parts for tiny imperfections that might have absolutely no effect on performance or safety? Where do we draw the line? How does the definition of a rejectable discontinuity change when our ability to perceive it increases so dramatically?
That's a huge question, moving from is it fit for purpose towards potentially is it absolutely perfect. That line and how industry defines it is going to be critical as these technologies keep advancing. Really fascinating food for thought. Thank you for taking this deep dive with us today. Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training and mentorship, or compliance solutions like NADCAP and FAA readiness. To learn more, visit amsl3.com. And don't forget to subscribe our YouTube channel for more insights and updates on non-destructive testing.
If you've made it this far in the podcast, I'd like to ask for your support. Please consider buying us a coffee. Your contributions help cover the monthly subscriptions we use to produce these NDT training videos and keep new content coming. We offer 3 levels of support. NDT Level 1, $1 per month, NDT Level 2, $2 per month, and NDT Level 3, $3 per month. Or a one-time gift of your choosing. Just scan the QR code on the screen to join and help us continue delivering updated NDT resources right here on YouTube. At AMS Level 3, our mission is to strengthen technicians and companies through consulting, training, and compliance solutions. Subscribe to our channel for more mentoring insights, share this video with your team, and give it a like to help spread the word. Visit us at amsl3.com to learn more about our services and resources designed for NDT professionals at every level. And a special thank you to Skaggs Media, the creative force behind these videos. Learn more at skaggsmedia.com.